In this video, we're going to use function mode in the TI-84 to find the zeros, factors, and intercepts of the polynomial function given here. And these are all related concepts here, as you'll see when we get through with this. So the zeros are simply the numbers that you plug it in for x and it generates a zero. They also turn out to be the first components of the intercepts. So once we get the zeros, we're going to know the intercepts, at least the x-intercepts. Now I'm going to be using the rational zeros theorem from college algebra. It tells me that if a polynomial has a rational zero, so a rational zero has to look something like p over q, where p and q are integers. So the rational zeros theorem tells me that if I have a polynomial with integer coefficients, which is what I have here, then if I have one rational zero of the form p over q, then p has to be a factor of the constant term, and q has to be a factor of the coefficient of the lead term. So it works like this. We take negative 10 and list the factors, all the factors that divide. Those are the numbers that divide negative 10. So it would be plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. And I look at the factors of the first term, which is 2. Now that if that first term had a coefficient of 1, then these would be the possible rational zeros here, the factors of negative 10. But guess what the theorem says? Okay, the factors of 2, plus or minus 1, plus or minus 2. Basically the factors, the zeros would be composed of, numerator would be a factor of the 10 over a factor of 2. So I take all these factors here and divide it by the factors of 2. All the factors of negative 10 divided by the factors of 2. All the possibilities. So the possible rational zeros, these are the possibilities. It might not have any, but if it has any, it has to be one of these. So possibilities are going to be plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. And then all the factors of negative 10 again divided by the other factors of 2, which is plus or minus 2. So each of these divided by plus or minus 2 again. So plus or minus 1 divided by plus or minus 2 would be plus or minus 1/2. And then plus or minus 2, next factor of minus 10 divided by plus or minus 2 over here. That's plus or minus 1, we already have it, don't have to list it. And then plus or minus 5 divided by plus or minus 2 would be plus or minus 5/2. And then plus or minus 10 divided by plus or minus 2 is plus or minus 5. We already have it. So if this has any rational zeros, it would have to be one of these. So we have a fifth degree polynomial. So at most we would have five distinct zeros, rational zeros, if it has any, for the real zeros here. So what we would do, we just pick one and just plug it in for x. Does it give me 0? Then it would be a 0. Then the next one, and so on. I'm going to start with the integers. And I'm going to take the calculator then, and here's what I'm going to do. Turn it on, and then go to variables here. Click on that, and then to the y, to the right rather. Variables there, and I want function, so I hit 1. And I could pick any one of those. I'm just going to pick the first one. So I'll hit enter. It's already highlighted. So if I evaluate this at 1, and I want you to notice here on the graphing screen, I've already entered this function. You see 2x to the 5th there, minus 7x to the 4th, and so on. That's listed. So I can just evaluate. I could also use this screen. That's another way. I think I've done that in another video. But I'm just going to evaluate this. I'm going to start with the integers. 1 first, so parentheses, and then 1. Hit enter. If this gives me a 0, then that's one of the zeros of this polynomial. Hit enter. It gives me 0. So I have 1 is a 0. And then I could just re-enter this again. Let me go to second and entry. And now I'm going to enter a minus 1. Do the next one, minus 1. Close parentheses. I'm evaluating the polynomial at negative 1. Hit enter. I get 0 again. So far I have 2 then. 1, negative 1 are rational zeros. And then the next one I'll go to is 5. So let's go second, entry. And let's just enter 5, hit enter, 0. So there I have 3 zeros. And then I let that, let's say, so then 1, negative 1, 5, and the other possibility, okay, is 2 and negative 2. So let's try 2. That one doesn't give me a 0. So 2 is not a 0. Hit enter. Let's enter a negative 2. Close parentheses. There it is. So 1, negative 1, 5, negative 2 are zeros. Now if I try 10 and negative 10, it's not going to be a 0, just to save some time. You can enter those, it's not going to be a 0. So then I have to go to the fractions over here. So let's try second, enter. And let me try 1/2. I'm just going to write it as 0.5. Hit enter, and it gives me a 0. So there we have 1, negative 1, negative 2, 5, and 1/2. We have all the zeros. So that's one way you could do it. Now the problem with this is sometimes they're repeated. So let's suppose you have a polynomial like this, and 3, say, is repeated 3 times. It's a multiple. Multiplicity 2, multiplicity 3. So yeah, you can do it again and again, and it's going to give you the 0, but you don't know if it's just one unique 0 or it's repeated. So sometimes you go another route. But in this case, there's no doubt because I did each one individually, and they're all distinct. So for sure, I know those are the only 5 zeros that this polynomial has. So if 1 is a 0, so just remind you here, if you know that R is a factor, if you know that R is a 0 of a polynomial, you know that x minus R is a factor. If I know that 1 is a 0, then x minus 1 is a factor. If I know that negative 1 is a 0, I know that x minus negative 1 is a factor. So x plus 1 would be a factor. And just to point out another alternative here, so you didn't have this calculator. Now you could always do it manually. You could always plug it in manually and compute it out and figure out if it's a 0. But you can also use synthetic division. So let's suppose I wanted to test these. Let's say I wanted to test if 1 was a 0 without the calculator. Then you just use regular division. Let's bring the 2 down here. Synthetic division, I should say. And then the way it works, say it's 1 times 2 is 2. Add these up, we get negative 5. 1 times negative 5 is negative 5. Add these up, we get minus 24. 1 times a negative 24 is a negative 24. 17 and negative 24 is negative 7. 1 times negative 7 is negative 7. 17 and negative 7 is 10. And 1 times 10 is 10. Go over to the last one here. And I add negative 10 and 10 is 0. If the last entry in this row is a 0, that tells me that 1 is a 0, or in this case, x minus 1 also would be a factor of the polynomial. And that's the way I would work it out. It is. So negative 1, I could do it the same way. And say I wanted to test another one, say 5. Instead of doing it manually, I could just bring this down here. And 2 times 5 is 10. Negative 10, or negative 7 and 10 is 3. Then 5 times 3 is 15. Add these up, we get negative 4. 5 times negative 4 negative 20. And then we add here and we get negative 3. 5 times negative 3 is a negative 15. 17 negative 15 is 2. And 5 times 2 is 10. Minus 10 and 10 is 0. If this last entry comes out to 0, that tells me that 5 is a 0 of the polynomial, which also means that x minus 5 is a factor. If this had been a negative, then it would be x minus a negative 5 or x plus 5. So now we have the factors. From that, we get the factors. And you could do that throughout. You wouldn't have to do a long evaluation or use the calculator. The calculator is quick. If the instructor lets you use a graphing calculator with that capability, then you can easily determine what the zeros are. So now, with that information, here's what we have. Using either synthetic division or using the function mode in the graphing calculator, we know the zeros are 1, negative 1, negative 2, 5, and 1/2. And we know the factors are, now here I wrote it in factored form, but the actual factors are x minus 1, x plus 1, x plus 2, x minus 5. This one you could write it as x minus a 1/2, x minus a 1/2. Same thing as this. If you set this equal to 0, and solve it, you get x equal to 1/2 would be a 0. And then the x-intercepts are the zeros. Well, the x-intercepts you get them from the zeros, because remember, when you replace the x by one of the zeros, in this case 1, -1, or 2, or 5, or 1/2, the y value is always 0. And that's your definition of an x-intercept. If the y value is 0, then that corresponds to an x-intercept. So if you were to graph this particular polynomial, it would cross the x-axis at 1, 0, -1, 0, -2, 0, 5, 0, and 1/2, 0. Of course, the y-intercept is usually obtained by replacing the x by 0. So put a 0 where the x is, you get -10. So if you were to sketch the graph of this, and we'll probably do this maybe in another video, replace the x by 0, the y value is -10. So the graph crosses the y-axis at the point 0 and -10. So this is the information we got. And you can see the relationship. You have the zeros, and from the zeros you can get the factors right here. See again, 1 is a 0, x minus 1 is a factor. -1 is a 0, x minus a -1 is a factor, or x plus 1. -2 is a 0, x minus a -2, or x plus 2 is a factor. 5 is a 0, x minus 5 is a factor. 1/2 is a 0. Then x minus 1/2 is a factor. This is the same as writing it this way. And like I said, from the zeros you get the first components of the x-intercepts. Another thing I want to point out to you, dealing with the graph, it wasn't asked here, but just it's something that's related. If you were to graph this polynomial here, we could use all that information we got, the x-intercepts, the y-intercept, but from this information, and because it's odd degree, and this coefficient here on the x to the 5th on the first term of the highest degree term is positive, I actually know that I can give the end behavior of the graph. So I know the graph is going to go up on the right side, and down over here on the other side, and then in between you could have several loops. But this is just the basic information that we obtain in order to eventually sketch the graph. In this particular video, we're not looking at the graph. Maybe in the next one. Thanks for watching, and we'll see you next time.